Hi everyone, my name is Neha and this is the 18th lecture on Introduction to Automation. In this lecture, we are going to learn about stepper motors. A stepper motor is a pulse-driven motor that changes the angular position of the rotor in steps. It basically divides a full rotation of the motor into a number of equal steps. And due to this nature of a stepper motor, it is widely used in low-cost open loop position control systems. If we see the step size, then it can range from 0.9 to 90 degrees. And here on the picture, it shows the basic stepper motor, which consists of rotor and the stator. So this center part, this is your rotor, and these four are the stator field poles. And the rotor is made up of a permanent magnet, and stator is made up of electromagnets. And these stepper motors, they are brushless in nature and have fewer mechanical parts. And because of their unique design, these stepper motors, they are inexpensive, and their design is very rugged, and they are easy to position. So here in this picture, let's see what will happen if the field poles are energized. Then in that situation, the rotor will move in such a way that it will try to align itself with the energized magnetic field poles. So if the field magnets are energized one after the other around the circle, the rotor can be made to move in a complete circle. And they move in steps based on the pulse sent to the stator winding. And due to this type of nature, the rotor basically it does not rotate continuously. And because of that, this type of motor does not have the horsepower rating because the speed of the motor is controlled by the frequency of the pulses. And most of the time these stepper motors, they work on a open loop control system rather than closed loop. Now next we are going to see the applications of stepper motor. Now before we see the application, we need to understand that these stepper motors, they cannot run at high speeds, but they do have a high holding torque. And these types of motors, they are beneficial in control type applications where without the need of the position sensor controller, it can determine the exact position of the motor shaft. And this can be done by simply counting the number of the steps taken from a known reference point. And these step size, they can be determined by the number of rotors and number of stator poles. Now, if we look the application, then these type of motors, they are used for precise positioning with the motor, such as they are used in hard disk drives. In robotics, they are used. They are used in antennas. They are used in CNC milling machine. So most of you have worked on a PCB CNC milling machine, and you know that how much precision is required in that machine. So there, the machine uses a stepper motor application, and because of that, the machine is able to have a precise control. And then this can be used in 3D printing equipment, textile machines, printing presses, gaming machines, in toys, in cameras for automatic digital camera focus and zoom functions, and there are many more applications where stepper motors can be used. Now next we are going to see different types of stepper motors. So there are three types of stepper motors. First is the permanent magnet stepper motor. Second is the variable reluctance. And third is the hybrid synchronous stepper motor. The permanent magnet stepper motor, it uses the permanent magnet in the rotor, and it operates on the attraction or repulsion between the rotor permanent magnet and the stator electromagnets. Second, which is variable reluctance stepper motor, it is made up of a plain iron rotor, and its operation is based on the principle of the minimum reluctance, which occurs with minimum gap. And hence the rotor points, they are attracted towards the stator poles. And then the third is hybrid synchronous stepper motor, and as its name suggests, it is a hybrid stepper motor, which means it utilizes the combination of a permanent magnet stepper motor and the variable reluctance stepper motor technique to achieve the maximum power in a small package size. So we're going to see all these stepper motors in detail. Let's first start with a permanent magnet stepper motor. In permanent magnet stepper motor, as I said before, the rotor is made up of permanent magnet. So here in this picture, this rotor is of permanent magnet, and it has been put into this position where the south side is faced towards the fourth field pole, and the north side is facing towards the second field poles. So these are the four field poles you see, or you can say that they are stator poles or they are electromagnets, you can say. So what will happen if we energize the coil 1, this coil, if we energize, or if we energize this stator winding, then what will happen? Then the south side of the rotor will try to align with this energized coil, and it will move towards right. So this south pole of the rotor will try to align to this coil once this is energized. And then what will happen when the coil 1 is de-energized? When this is de-energized, at that instance the coil 2 is energized. Okay, so case 1, when the coil 1 was energized, at that point this rotor moved towards the right. And in the second case, when this coil is de-energized and this coil is energized, then what will happen? Then rotor will again try to move towards this coil, towards this energized coil, and try to align with this coil. And so in that situation, the rotor pulls itself into alignment with the coil 2, and thus the rotor turns in 90-degree steps for each successive excitation of the field coils. Now let's say if you want to change the direction of the rotor, then how will you do that? It's pretty simple. You will just change the direction of the energizing the coil. So for example, let's say coil 4 is energized first. So your rotor will stay in this particular position. And in the second case, when coil 4 is de-energized and at the same time coil 3 is energized, then in that situation your rotor direction will change towards the left, which means the south pole will be facing towards the third coil and the north will be facing towards the first coil. And the step size here, based on our this example, is 90-degree steps it is taking. So you will continue this process. So first this was energized, and then this was energized, and this was de-energized, and then in the next cycle the coil 2 will be energized, and at that time coil 3 will be de-energized, so the rotor will move towards coil 2, and then further coil 1 will be energized and coil 2 will be de-energized. So in this way the rotation will take place. Now here, one important property of the permanent magnet stepper motor is that the rotor will tend to align up with the field pole even when there is no power applied to it. Because of the permanent magnet rotor will be attracted to the closest iron pole, due to which there is a magnetic tuck which can be observed. So this magnetic tuck is also sometimes called detent torque, which you can see here I've written. And there's another name of this is residual torque. So three names actually, detent torque, residual torque, or you can say a magnetic torque. So this detent torque, it is a desirable property in many applications because it tends to hold the motor in the last position. It was step 2, even when all the power is removed. Now let's see the effect of load on stepper motors. In this, we are going to learn the concept called stalling. So before we understand the stalling, we need to know that in the open loop, in the open loop, that concept works when the command is supplied to the motor, and based on the command, the motor it moves a step, or you can say it provides a step change whenever it receives the command. Okay, so that's how the open loop works. And in some situation, when the load is large, then the motor may not have enough torque to make the step change. So in that situation, the rotor would probably rotate a little when the step pulse is applied, and then fall back to its original position. So this is called your stalling. And if the feedback is not used, then the controller will not know which step has been missed, and that's why in some cases the feedback is used, or you can say the closed loop controller is used, which can provide the feedback to the system that the step is missed, and based on that it will work accordingly. So here in this picture you see this is our rotor and this is our stator pole, and we are assuming that this stator pole is energized. So if it is energized, then what will happen? Then this rotor will try to align with this energized stator pole, and it will move towards the left. So the south pole will try to align with this stator pole. And as the rotor pole approaches towards the field pole, the attraction force gets stronger, but the torque component, it gets weaker. So you can see in this last picture, so it is moving, so this rotor is moving and it is further moved away towards the field pole. And then in the last picture you can see the rotor is actually aligned towards the field pole, and at this particular situation the torque is very small, or you can say torque is actually zero. So in this we observe that the maximum torque basically occurs when the rotor is somewhere around 45 degree away from the field pole, and if the load is greater than this maximum motor torque, then the rotor will quickly slip to 90 degree behind, and this might cause the motor to take a step backward instead of going forward. So in that situation, this rotor will go back to this previous position. Now, next is this is a case. Let's consider the situation in where the rotor has been stepping counterclockwise, and we have allowed it to lag a full step behind the energized pole. In this particular case, you see that coil 1 is energized. So if the coil 1 is energized and if your rotor is in this direction, then what will happen? Then rotor will try to align with this stator pole. The south pole of the rotor will try to attract with the north pole of the stator winding. So it will move towards left. Now let's see this figure B. In this figure, we see that coil 2 is energized, and this is the position of the rotor. And if the rotor is positioned in this way, and if coil 2 is energized, then what do you think will be the direction of the rotor? In which direction it will move? Is it going to move in the left direction or in the right direction? This is a difficult situation because you see these are two north poles. So this we know that south and north pole attract. So this south pole of the rotor will have to move somewhere. So in this particular situation, there will be little or no torque exerted, and this is like a balanced condition. So rotor will equally attract in either direction. and it cannot reliably predict if it will turn clockwise or in a counterclockwise direction. So for proper operation, the rotor lag must not exceed 1/2 the step size, which would be 45 degree for the motor. And if this happens, then the problem will be solved and the motor will always turn in the direction it's supposed to, and it will not stall. So this is the end of the lecture. Thank you so much for watching.